So what we're talking about is glomerular filtration rate. GFR. And essentially, it's how quickly you're making urine. And just as a preview, why you care is because if you make urine too fast, you're basically going to start flushing things out that you don't want to lose. You're going to lose too much water, and you're going to dehydrate yourself. You're going to lose too much sodium, calcium, and potassium. That's going to be a problem, because think of how many times you put sodium, potassium, and calcium in this glass. So you don't want to lose control of that. On the other hand, you can have a problem of I'm not making enough urine. In that case, you're not getting rid of waste products. So the problem here is you can have making too much urine, not enough urine. You need to hit the Goldilocks, so to speak, right? You need it to be just right. The problem with that is out here in the rest of my body, my blood pressure is going up and down. If I'm sleeping, my blood pressure might be 100 over 60. If I'm running on a treadmill, it might be, you can laugh at that. If I'm running on a treadmill, it could be 180 over 100. So my blood pressure, thanks, Ms. Myers. Your blood pressure can be shifting quite a bit. It's like Henniger hasn't been on a treadmill in. Just kidding. So anyway, so your blood pressure can change a lot, but your kidney can't have that, because all of a sudden if your blood pressure goes up, you're going to make too much urine. You're going to get rid of fluid that you want to keep. You're going to get rid of sodium, potassium, and calcium. Or if you go to bed at night, it's much easier to picture Henniger on the couch or taking a nap. Henniger's on the couch taking a nap, your blood pressure plummets, and now your kidney's not doing anything. So that's the preview of why we care about this. The first thing we're going to do is we're going to put up a somewhat horrible approximation of the glomerulus. So this is the glomerulus, the tough.
How big should these be?
What's that?
How big should my glomerulus be?
So this is a scan of an 11 by 17 sheet of paper, so the same size of paper you have. So you need to write a little bit small, and it is going to get filled up. This right here is the afferent arteriole. So this is bringing blood in, and this is the efferent arteriole. So this is blood moving. It's not a huge important number, so I'm going to put it in kind of an off color. But you generally, when you filter everything smaller than a protein, you end up filtering about 180 liters per day. So blood comes in, everything smaller than a protein is filtered. About 30 times your blood volume is filtered a day. And so you make about 180 liters of what's called filtrate. Later on, once you've picked up everything that you don't want to lose, and this is ready to go down into the bladder, that's when it's called urine. You have to have something to pick this up. So the first thing we're going to draw is Bowman's capsule. So this is Bowman's. Trying to put in a little bit of a wiggle, because that's going to be the proximal convoluted tubule. Try to put in a little bit of a loop of Henle, because the loop of Henle dives down towards the deeper portions of the cortex. So this is the loop of Henle. This over here would be the distal convoluted tubule, and I was very deliberate about bringing my DCT back up next to the afferent and the efferent of the glomerulus. And then I wanted a cross section here, so that's why I put in this kind of little structure. But then we're going to keep going. This would be the collecting duct. And then whatever makes it here is going to be urine. So it's two ureter. I mean, technically through the calyces, through the pelvis, into the ureter. I keep saying everything's smaller than a protein, but let's get some of these things up here so we're very specific. One of the first things is going to be water. A lot of water is going to be filtered over here. one of the things I would like to note is there's a lot of water that's filtered, but we're going to get rid of that. We're going to get that back out of here because we want it. So by the time we get over here to where it's going to be urine, the water level has considerably dropped. So this would be water. Other things that are in here are glucose. So glucose, I'm being fairly specific with two. Glucose is smaller than a protein, and so that will get filtered over. There will be lots of glucose over here. But hopefully that glucose is taken back up by the time you even get to the loop of Henle. Now in an American diet, you don't necessarily need to worry about spilling glucose out into your urine. But if you're an animal in the middle of winter, and it's hard to find a plant, so we're in Iowa, so I think of a deer. Deer has to search hard for glucose in the middle of winter. So you would not want that animal would not want to be urinating out glucose. So even though glucose is filtered, you can get that glucose out of there before you get to the loop and get that back into you. Pink's not a very good color, but it's just for small items. We're just going to group some things together here just to point out. It could be vitamins, minerals, small proteins or amino acids. When I say filter everything smaller than a protein, I mean kind of large protein.
Does it go all the way through? Or just
Nope.
stop for the...
That should stop too. Because again, you don't want to really lose vitamins, minerals, and small proteins. Now if you're consuming mega doses of vitamins, then the way your body gets rid of that. So if you take a mega dose of vitamin C, you'll just urinate out more. So there could be vitamins over here depending on your dose. Things like sodium. The sodium is going to be very concentrated in here. It's still going to be concentrated when you get to the loop of Henle. But by the time you get to the loop of Henle, the concentration has diminished. Now there will be some sodium out here because you consume sodium in your diet, and so you need to get rid of that in your urine. But most of the sodium will be taken out at the PCT or also at the loop of Henle. Now you might ask, where is this stuff going?
Wait, what did I just...
Say what?
What were those at? I just drew.
Oh, thank you. Sodium. You might ask, where is this stuff going? And you say, I need to pick it back up. I don't want to lose it. Where it goes are the peritubular capillaries. Come off of the efferent. And wind around. So these are the peritubular capillaries. And they're going to wind around, pick up things that you don't want to lose, and then head back to the systemic circulation. So things like glucose, they're going to head back into the peritubular capillaries because there are transporters. They're going to pull this glucose, pull, push. They're going to take this glucose out of the filtrate and get it back into the blood. Similarly, there's going to be transporters. Really, it's the sodium potassium ATPase again. we're going to transport sodium back into the blood. So pull it out of this filtrate and put it into the blood. Same thing for everything, vitamins. Now, a key thing we're working on is that these transporters are not perfect. And they really just work at one speed. I mean, there's some variability, but for the most part, they work at one speed. And what that means is if GFR is too high, then everything will go by those transporters too fast, and they won't be able to pick it up. So you'll end up with some of this good stuff like vitamins and glucose and extra water out here in the urine. That would be a bad thing if GFR is too high. Another thing, another bad consequence is these would be urea, or you could just simply say waste products. Ideally, you want everything that's filtered that's a waste product to stay stuck in this tubule so that it makes it into the urine. The problem is a lot of these waste products are lipid soluble. And if you go way back to AP1, hopefully you'll remember that if something's lipid soluble, it can pass through a plasma membrane. Which means, since this barrier here, this tube wall is made of cells and plasma membranes, something that's lipid soluble can leak back into the peritubular capillaries. So if it's lipid soluble, it can go through the cell it's making the peritubular capillary. Sorry, it can. So if it's lipid soluble, it can go through the cell that's making the proximal convoluted tubule wall. And then it can go through the cell that's making the wall of the peritubular capillary. And so things that you don't want to make it back into the peritubular capillaries will have a chance to leak back in. So to get this written down, the point I'm trying to make is that GFR has to be tightly regulated. GFR is closely regulated. The reason is, if GFR is too high, good things are lost to the urine. So if GFR is too high, all of this stuff goes by these transporters too fast, so it's pushed past those and it ends up over here. You're going to urinate it out. And you may think, well, that would be bad because you're going to lose glucose, but maybe I'll just have a Snickers bar to make up for it. Or maybe I'll just eat more vitamins. But the bad thing is you're going to lose control of water and sodium. So the main thing is you lose control of water and electrolytes. You can dehydrate yourself. You can throw off your sodium, potassium, and calcium concentrations pretty quickly. And again, think about all the things those control. If GFR is too low, waste products make it back into the blood. So then, why filter at all if you're going to let all the things you're trying to get rid of have time to get back? So I'm going to be redundant because it's better to be bored than confused. But again, if GFR is too high, everything goes through too fast. Good things, including sodium and water, that over here you've lost control of sodium and water. If everything goes through too slow, then all these bad products, waste products, have time to leak back and get into the low. The easiest metaphor for me is the I Love Lucy episode, Lucy at the Chocolate Factory. So for me, the metaphor is if everything, like the chocolate off the end of the conveyor belt, if everything goes through here too fast, you're going to lose good things that you want to keep. And so that's why GFR can act too high. Something that's going to add complexity to this, though, is the pressures that are driving the creation of this filtrate are relatively small. Small at least in compared to systemic fluctuations. And so even though this control has to be very, very tight, it's even more complex because the variances, the pressures that it's operating under are very, very small. So what I'm going to do first, I'm going to draw something we've drawn before. And I wouldn't necessarily draw it, to be honest. Unless you want to put it on the back side or something like that. But you've seen it before, because what we're drawing is capillary dynamics of fluids, or fluid capillary dynamics. And we said that when we did this, we said this is an arteriole, we said this is a venial, and we had two pressures. We had something called HPC, which is usually around 35 millimeters of mercury at the arterial end. So this was essentially blood pressure. And that drops at the other end to something like 18 millimeters of mercury. The other pressure we had operating here is the liver makes something called albumin. And albumin will come back up when we talk about pH. The main thing this albumin does is it's an osmotic agent. So water wants to move towards stuff. So if you fill your blood with albumin, it's going to generate a draw. We call this OPC. And that was 25 millimeters of mercury. So I'm just putting these on the board just to kind of link the pressures that are happening in here with knowledge you hopefully already have, which is nice. Over here, we have something very similar to HPC. But whereas here the C stood for capillary, this is going to be HPG. And it's going to stand for hydrostatic pressure. Of the capillary. And here it's going to equal about 45 millimeters of mercury.
G is from glomerular. HPG.
Thank you, thank you. It's HPG, hydrostatic pressure of the glomerulus. Thank you. Hydrostatic pressure of the glomerulus. Just like we have an osmotic pressure here, this albumin is still in here. But also, since you're filtering everything smaller than a protein, there'll actually be even more protein in here. This is going to be OPG. OPG stands for osmotic pressure of the capillary. Just kidding. Osmotic pressure of the glomerulus. Over here it was 25. Here again, because there's a little bit more because you concentrated with the protein by filtering everything smaller than a protein. It's going to be a little higher here. It's going to be 28 millimeters of mercury. We have one more pressure here that we didn't have here, and that is because this is a confined space. And fluid that's already in here It doesn't want more fluid coming over, and so that's going to push back a little bit. Out here in a capillary, you really don't have a confined space because any fluid that you pushed out there can just be absorbed by the fact that there's so much volume out there. But here, any fluid that's moving this direction is going to fill this capsule and push against the fluid that's coming back in this direction. So there's a small pressure pushing back in that direction, and this is called hydrostatic pressure of the capsule. So it's kind of confusing because this one's called HPC, just like this was called HPC. But here HPC stands for hydrostatic pressure of the capsule. And it's a small pressure. It's only about 7 millimeters of mercury. And I should say these pressures are going to be different in any textbook that you look at. But the general idea is that HPG is the large pressure pushing filtration out. Resisting that or pushing back are OPG and HPC. If you add these up, we should actually probably put a negative sign in front of the 28 because it's going the opposite direction. And we should put a negative sign in front of the HPC, which really is just stating HPG is going this way, OPG and HPC are going in this direction. The net results, so the net you know what, I just realized I wrote down wrong number.
You are.
This should have been 10. Sorry. It should have been 10. I messed up your whole diagram, didn't I?
Yep. No, one sec.
Would you be more mad if I told you I did that deliberately so you have to redraw? I'm kidding, I don't. Sorry. The reason it took me that long is because I know the net filtration pressure is what 7. Net filtration pressure, 7 millimeters of mercury. So the net filtration pressure equals 7 millimeters of mercury. Now that should be concerning, because if we just kind of threw some numbers out here, DJ goes for a run, maybe his blood pressure goes to 180 over 120. DJ naps on the couch, his blood pressure drops to 100 over 70. DJ's up teaching a class, and so his blood pressure goes to 130 over 90. My systemic blood pressure is changing a lot throughout the day. It's changing by 80 millimeters of mercury or more. HPG, which is essentially blood pressure, cannot change by that much. If all of a sudden this number doubled or went from 45, so like this number is almost doubling, if this number almost doubled, then I'd be making lots and lots of urine. It's actually estimated that you could go, if you didn't have this control mechanism, you'd have to urinate something like 40 liters of urine a day, which I wouldn't really go down that path very far, but imagine how your life would be different if you had to urinate 40 liters in a day. So I smirk because there's this author named David Sedaris. He talks about how when he's at book signings, he didn't want to have to get up and interrupt people to go to the bathroom, so he got himself a stadium pal, which is basically a catheter bag that you put inside your pants, and he said it was really challenging to try and go to the bathroom while looking someone in the eye. Anyway, we'd all have to have a stadium pals if we didn't make sure that this blood pressure does not change with this blood pressure. So the rest of all this drawing is how do we keep GFR relatively constant by isolating this blood pressure from this blood pressure. I'm going to erase this now, and we're going to go across this board But I'm going to try and keep things relatively tight so that I can get it all on the camera. So I might steal a little space here too. So we've got 4, maybe 5 mechanisms. And I say 4, maybe 5 because I'm going to add one. But the first 4 are the main ones. The first control mechanism is myogenic control of the afferent and efferent arteriole. We talked about this before because we said that myogenic control is a method of autoregulation. And autoregulation is when a blood vessel can control its own blood flow. And we talk about 2 different types. We talk about metabolic and myogenic. Metabolic was DJ's in the gym working his biceps. Those capillaries might experience low oxygen, low ATP. So the precapillary sphincter doesn't have oxygen and ATP to stay constricted. So it opens up and blood starts flowing to the capillaries in his biceps. That was metabolic control. And we said there's this other control mechanism. It's a little bit harder to understand, but it would be important when we got to urinary, and that was myogenic control. What myogenic control is, let's see if I can sneak it up here, is if you have a blood vessel that experiences a drop in pressure, you would think what it's going to do is constrict to get that blood pressure back up. But it will actually, in myogenic control, dilate. And again, what you have to break yourself of, or at least I have to break myself of, is you think you want blood pressure to stay the same. But there's a couple of situations where you're more concerned about flow. You want the same flow rate. So if you have a decrease in pressure, but you want the same amount of blood going through this vessel, you need to dilate in order to help the blood get through that vessel. On the other hand, you see an increase in pressure. If you think, well, if I have an increase in pressure, I need to dilate to get that pressure back down. But in myogenic control, you want the same amount of blood going through that vessel. If you have an increase in pressure, more push, you need to constrict so that the same amount of blood is flowing through there. So it's the opposite of what you might intuitively think. But the take-home message is if you dilate with decreased pressure and constrict with increased pressure, the amount of blood flowing through there is going to be roughly the same. So I'm going to draw 2 little graphs here. The first one just says this little ramp is supposed to be pressure. So that's high pressure and low pressure. In high pressure, the blood vessel will constrict. In low pressure, the vessel will dilate. The net result is that blood flow stays the same. It's easy to understand that in your brain. Your brain has to have blood flow. So if you have low pressure, the vessels taking blood to your brain have to dilate to make sure you still get flow to your brain. Or if there's an increase in pressure, you need to constrict so not too much blood flows to the brain. So essentially what you do is you change vessel diameter to keep flow the same. The way it works in the afferent and the efferent is I'm going to draw 4 cartoons here really quick. The first one, I'm going to draw a dilated afferent. So this would be the afferent. I'm going to draw a dilated afferent. So if you dilate the afferent, you've now got more blood coming in. So that's going to increase filtration. You could also, I might might draw them all the way across. Constrict the afferent. So now there's not as much blood coming in. So you're going to decrease filtration. You could do the same to the efferents. So here I'm dilating the efferents. I think about the efferent as an escape route. And so if blood comes in, it can either be filtered or it can go out the efferent. So this is going to decrease filtration. So blood says it's easier to head out the efferent than it is to be filtered, so it just heads out the efferent. Or you can constrict the efferent, in which case the blood cannot really leave to the efferent, so you increase filtration. So you can affect filtration quite a bit by dilating or constricting the afferent, dilating and constricting the efferents. And overall, if we put blood pressure here, we just put blood pressure in increments of 40, and you look at GFR on the y-axis, there's a huge range of blood pressure where GFR stays the same. So as long as it's up to 80, GFR is the same as all the way up to around 200 millimeters per mercury systolic blood pressure. The second mechanism are cells called Juxtaglomerular cells. Or JG cells. And these cells are mechanoreceptors, or they're stretch receptors. Mechano stretch receptors. And where they exist are around the afferent. And there's some around the efferent. So they're little stretch receptors that hang around the afferent and the efferents. What they do is if low stretch, that means there's low blood pressure. And if these cells sense a low stretch, it means there's not enough blood in this afferent. And that's going to lead to a problem of low GFR. So what they do is they release something called renin. And we're going to come back to renin because it's a little more complex than we're putting on the board. But at this point, you can think of renin as increasing sodium absorption. So you're going to absorb all of the sodium, or as much as you can. You're going to absorb more sodium and excrete less. That's going to cause you to get thirsty, drink more water, and that's going to raise your blood pressure. The other thing renin can do is stimulate systemic vasoconstriction. So it can cause all your blood vessels to constrict, and that's going to raise your blood pressure. So if these guys sense low stretch, it tells them blood pressure must be low. We don't want blood pressure to be too low, because if GFR is too low, waste products are going to leak back in. Let's raise blood pressure by absorbing sodium, because now we'll end up absorbing more water, or we'll get thirsty. And also to stimulate systemic vasoconstriction here, so your blood vessels will constrict. If they sense increased stretch, that must mean blood pressure has increased. So now let's do the opposite. So let's stop releasing renin. So renin is released on kind of a continuum. You can either release more or release less. So in this case, release less. So that will decrease sodium absorption. And it will also lead to systemic vasodilation. The third type, called Macula Densa cells, or MD cells. I'm trying to be tight so it all fits in. Macula densa cells are osmoreceptors / sodium receptors. They're essentially sodium receptors. And where they hang out is in the wall of the DCT. Right as the DCT comes up between the afferent. These cells are going to influence JG cells, so they need to be in close proximity to JG cells. So macula densa cells are in the distal convoluted tubule at the afferent and efferent. These guys are always the ones that are more difficult for me to follow, because what they do, and maybe I'll just talk it through really quick. So they're going to look at sodium right here. By looking at sodium, they can figure out, is the GFR correct? So there should be a lot of sodium here, and there should be some essentially equivalent to diet out here. Whatever you ate, you need to get rid of. Now, if the MD cell sees too much sodium, it means the sodium flowed through here so fast that you weren't able to pick it up, and therefore you have a high GFR. If sodium here is too low, it means that sodium flowed through here. It went through so slow that it all got picked back up, and so GFR is too low. So over here, if sodium at MD is too high, that means GFR is too high. Because I was supposed to pick up some of this sodium, get it out of this filtrate. But everything went through so fast, couldn't pick it up. And so now there's too much sodium over here. So the problem is high GFR. So what you can do then is inhibit GG cells, which means you're decreasing renin. And you can rewrite this, but to be honest, the reason I draw this all out is so you start seeing these connections. So that's what's going to happen. Sodium absorption is going to go down, and you're going to cause systemic vasodilation. And that's great, because if GFR is too high, the problem is probably that blood pressure is too high, and you're pushing too much blood through here, making too much filtrate. If sodium at MD is too low, that equals a low GFR. So now all of this filtrate moves so slowly that all of the sodium was taken back into the blood. So there's not any sodium here. It means GFR is too low. If GFR is too low, we're going to stimulate GG cells, which will increase renin. The other thing that MD cells can do, and it's why all of this is in here so tight, is they can also alter the diameter of the afferent. So if your GFR is too high, the quick fix is to constrict the afferents. So MD cells can also constrict the afferent. So here again, look for connections. Now this is going to get really messy. If you constrict the afferents, you're going to decrease filtration. And that's exactly what you'd like to do if GFR is too high. Down here, you can dilate the afferent. Dilating the afferent will correct this decreased GFR by increasing filtration. So we have one more, and then kind of a fifth one that you might see depending on where you read. Do the fourth one though. The fourth one is the autonomic nervous system. And specifically, it's the sympathetic nervous system.
Another room.
Say what? This one's a small one. You can fit it right there or right down there. The autonomic nervous system, specifically the sympathetic nervous system, can control afferent and efferent. If you want a slow rise in blood pressure, like Henniger keeps talking about how this test is in 2 weeks, and then next week I'll say it's in 1 week, I'll say it's next Tuesday. So if your blood pressure is slowly rising, the way it's doing it is you're going to constrict this afferent slightly. And by constricting this afferent, you're going to make less filtrate. You're going to make less urine. You're going to go to the bathroom less, but you're going to retain fluid. and that's going to raise your blood pressure. I don't know that you necessarily need to write that out, but what will happen is constrict afferent. What that will do is decrease filtration. That will lead to fluid retention. And that will lead to a slight increase in blood pressure. I lied to you, didn't I? You don't really have to put all that. The other thing that the sympathetic can do, if I put one there, is it can also control renin. So it can stimulate or stop renin, which means it can affect sodium absorption and blood vessel constriction. The last one I want to put, I'm going to just put it over here, because I don't always put it, but then somebody on YouTube pointed out that I've forgotten the Sanjo cells, but I want to add those. In case you're reading a good textbook, you might come across these. Sanjo cells are the cells that actually make the pores in the filtration membrane. I don't know that this has been known for long, but it seems like the size of the pore changes with blood pressure, which is brilliant. If you have an increased pressure, then the pore becomes smaller. Decreased pore. And that would cause a pretty quick decrease in GFR. If there's a decrease in pressure here, we want to keep our GFR up. The pore widens or increase the size of the pore. And that will increase GFR. I don't think it's in our textbook, but it's in the textbook that I tend to read, and I'm going to point this out if I've never mentioned this. A really awesome textbook, I'll just put it right in the middle, is Textbook of Medical Physiology. By Arthur C. Guyton. When I got my degree in neuroscience, I took the first semester of medical school, and so this is the first year medical school textbook, which you're like, oh, why do I want to read that? I actually think this one probably reads better than your textbook. It goes further and deeper than yours, but it actually reads better and it's more understandable. So if you're looking for a textbook where you really, really want to know your physiology, that's an awesome textbook. It's probably not even the best medical school textbook, but it's just highly readable, so the balance is really nice. So if you can get a copy of that, that's a great book. Other than that, this is all you need to have down, but you're asking right now is, do I have to reproduce this on a test? And the answer is no, you're not. You don't reproduce this on a test. But some of the things that are going to come up over and over when you're looking at your charts are the size of the afferent, dilate, constrict the afferent. Renin is going to come up over and over on your charts, and MB cells are going to come up over and over on your charts. I would say that if there's one section where you want to get the big picture and not just memorize it, this is probably the section. Questions?